All right, so welcome to computer graphics today. We're going to talk about 2D and 3D representations. And so what we're going to do here is kind of go over how do you represent basically models, whether it's in a two-dimensional context or a three-dimensional context. So there's kind of a theoretical basis behind it. And also, you know, what's kind of the practical way that we can deal with that. So anyways, yeah, we're going to cover the two-dimensional and the 3D side, and then talk a little bit about different applications where these are all useful. So let's go ahead and start with 2 dimensions. So one of the ways it's useful in two-dimensional graphics that we're interested in is sprites and tiles. All right, this is we're going to exclude basically writing just straight pixels to the screen. That's certainly an option, but when it comes to representing ideas on the screen, these two particular have been very popular. So the other kind are polygons, where we can just draw geometry straight onto the screen. And we can also talk about curves and shapes. Now we'll talk about curves and shapes just a little bit in this presentation, but we'll get into the details of how you actually do curves and shapes in a later lecture. So when it comes to sprites and tiles, we basically would like to deal with them in a way that's kind of agnostic about the representation that they're going to ultimately show up on the screen, right? And so this enables us, you know, I mean, I guess the background on this is that we have, you know, older console hardware when it was very difficult to get the right amount of CPU cycles just to draw pixel by pixel everything you needed to. Okay, so if you're talking, say, a 1 megahertz CPU, and that gives you about 30,000, 33,000 clock cycles per frame, roughly, then that means that if you're going to, say, draw a 320 by 200 image, you're pretty much you have to have 1 clock cycle per pixel, which is just not practical. So you have no way of doing that. So what hardware vendors have done is, how can we accelerate this, okay? And so with a sprite, for instance, we might actually use a common memory to store all of the raw imagery for both tiles and sprites. And then what we'll do is we'll just use an index into that. So we might say the sprite size or tile size is, say, 8 by 8. And so you can refer to any of those 8 by 8 indexes or indices and use that to draw. So instead of having individual sprites and with their own data, we basically eliminate the redundant data and use these indices to go ahead and reference to it. So for instance, this sprite data structure here might have X and Y. So where is the sprite located on the screen? The tile index would be which one of those 8 by 8 cells gets to be drawn in that area. The palette index would be, maybe we don't have a full RGB capability for each sprite. So we might say, well, every tile refers to, you know, can get its own, say, 4 colors or its own 16 colors. Okay, and that helps reduce the memory footprint by quite a bit. And then sometimes you'll find some additional hardware-based acceleration for flipping the sprite. So you can flip it vertically or flip it horizontally. And then you can set a priority. So should this be drawn, should other objects draw over this one, or should we draw this on top of other things? Or should this be drawn on a background layer or maybe the front layer? Okay. And so tiles represent kind of the same idea. We might actually have essentially a grid of tile numbers. We basically say this two-dimensional grid of numbers represents all the tiles for the screen. And we might need to specify an X and Y. So if we want to scroll that background, we can specify where that whole tile layer is. And then we can specify the width and height. So how many columns and how many rows of cells are we utilizing? And then of course we would need a list of the palette colors, and the palettes would just be an index, 0 through whatever. So using this, you can, a lot of graphics from the 80s and early 90s have been used just using this this style, and because it's all integer math, makes it very easy to speed up, and it makes it very efficient for low, you don't have to have a massive hardware budget to handle this kind of, I guess, paradigm. So polygons would be the next thing, right? We would like to be able to draw polygons on the screen, and this is a little bit more when we're talking about vector graphics. So over here, it's more raster graphics because we're dealing with pixels. Polygons are more vector graphics because they can scale to the size of the screen. So fonts would fall into this category because they're basically just descriptions of, points, maybe color, and you can extend this to include curves and shapes, where instead of just using the actual points on the polygons and lists of those vertices, then you could say, well, we actually have control points, and we can smoothly draw from one point to the next based on some parametric equation, or we use some kind of polynomial expression to kind of handle that. All right, so we'll talk more about curves and shapes in the future, but we just kind of want to, think about, if we're doing 2D graphics, what are the two ways of doing it, right? So this is basically 2 ways of doing it. We could basically use sprites and tiles, or we use polygons. And so moving into the 3D polygonal representation, now it gets a little more complicated because, from a data structure standpoint, we'd like something to be flexible for nearly any kind of need we have. So here's one particular representation. Essentially, we have a bunch of objects, and we'll just use the word object in a general sense. The things, for example, the things in this room, right? Things inside of a scene. And we could break down an object by saying that we're going to compose it out of surfaces. Now, this is a, we'll take a quick detour here just to kind of talk about that this is typically different than what computer-aided drafting does. Computer-aided drafting often approaches it from the perspective of, we're not dealing with surfaces, we're dealing with solid objects. So we'll use a different technique called constructive solid geometry, which we can basically construct. We can either subtract whole objects out of each other or merge 2 objects together such that they're a brand new 3D, it's not a surface, but a 3D actual object, okay? This is different though than what we've been studying because we've been learning how to draw polygons, right? And polygons are surfaces of objects. They don't represent the inside of the object. So I just want to make that quick distinction that we're going to kind of take a split here, and we're going to ignore the solid-based modeling options for now. Okay, so we have surfaces. So basically, if we were to take the cylinder, a surface is going to represent both the cylindrical area, right? So we basically want things that have area, and then the top and the bottom, all right? So we would say that now we have our object. It's really just a bunch of surfaces put together. And once we have these surfaces, this still not, we haven't really quite talked about tessellation and how do you go from a surface to having polygons, right? We can't just simply go from surfaces to pixels. So what we'll do is we'll turn these surfaces into polygons. So over here I have a roughed out version of this a cylinder, because polygons essentially approximate the surface geometry, okay? And but what makes it nice is that for one, they're composed of edges, and this can become useful later. And edges will connect 2 vertices, all right? So at this point, we're thinking about, from a data structure standpoint, how can we store this, this idea, okay? So the edge looks pretty simple. We might use a pair and use 2 vertices or indices to 2 vertices for the left side and the right side. The polygon is basically going to be a list of edges, so how do you go from edge 1, edge 2, edge 3? The surfaces are going to be a list of these polygons, and objects are just going to be a list of surfaces. So you can kind of think in your head, how might we create data structures out of this so we can work with them? So here's one particular, some details that we might consider. So the overall data structure, we might just have a list of vertices, a list of edges, and a list of surfaces. And this is basically to consolidate everything so that we don't have a mass, I guess, replication of data. But we're gonna, we'll talk in a slide, the next slide, that you do want replication. You don't want replication of data if you want certain kinds of behavior. Okay, so kind of thinking about how we would do this with OpenGL, we might need some kind of mode. Is this going to be a bunch of lines? Is this going to be a bunch of triangles? Is this going to be a bunch of rectangles? What kind of surface is this going to be, right? And then we have our indices, which are more or less, so we have this count, type, offset, material. Those are all properties that will help us draw the surface. Okay, so for example, the indices might just represent a list of all the actual indices for that surface. So rather than replicate the vertex data over and over again, all right, if it's triangles, we wouldn't want to say vertex 0, vertex 1, vertex 2, vertex 0, vertex 3, vertex 4. We could say, well, vertex 0 is being duplicated at least once there. So what we could do is, instead of saying use that entire vertex structure we talked about last week, just use an index, an integer index that will then point to the actual structure in memory. And we looked at the buffer data, OpenGL, the buffer objects, and it makes sense to be able to just kind of throw all of our vertices in this contiguous chunk of memory, and then we can use indices to index into that. So that's what we can use with the surface structure, is all the indices that relate to the surface. And then we can store the vertex information as another array, and that's the data we would send into the buffer object. And then our edges, we can store, just first and second. So if you're just thinking like the standard colon pair, we got first and second, then that would be adequate. Okay. Now, when you're just doing plain graphics, last week we showed how to draw a polygon. We didn't have any edge information. If you're not using edges for a particular case, like you don't want to say draw like cartoon rendering or outline rendering, then you don't need to store edge information. It's not essential. But if you do want to store edge information, then it'll be important, because it's hard to determine without using some kind of image analysis algorithm whether or not you're looking at the contour of an object, or whether you're looking, or whether two polygons facing you is that seam between the two polygons, is that actually supposed to be a visible edge, or should that be something that's hidden? Okay, so we might need some information that tells us whether we should draw the edge or not. And so some 3D software packages will allow you to customize whether that edge is visible specifically. So if you were doing a 3D model of say a human face, right? And you have some contours on the face, like the lips, right? That you want to maybe be drawn out. Maybe you're doing like cartoon rendering. So you could probably specify the edge on the lip and say, always draw those edges. It doesn't matter what angle you are. And then the rest you can say, only draw it if it's a silhouette. Okay, so let's look at the usefulness of this edge list. So this is something that you can accurately determine the silhouette edge. So let's just say that you have two polygons, and they all have a normal associated with them. So you have two directions, and they share an edge, okay? And so you can take that edge, and it has the information of which polygons on the left and which polygons on the right. And then what you could do is you could take the dot product between the normals of the polygons and with the camera direction and determine whether or not they're front facing or back facing. All right, front facing means the polygon faces towards the camera. Back facing means they face away from the camera. Well, it should be, and we know that the dot product will be positive if the if the normal and the camera direction are within 90 degrees of each other. All right, so at 90 degrees you get 0, and as they get closer and closer to being parallel to each other, then you get close to 1, right? Because cosine of 0 degrees is 1, and cosine of 90 degrees is 0. Now, as soon as you go past 90 degrees, then you get negative numbers. Okay, so then it starts going from 0 down to -1 if you're at minus 180 degrees. So the range of cosine is particularly helpful here, because then we can take the sine of those directions, and if they're facing the wrong, if they're both the wrong direction, then you know one face is facing away from the camera, you know one is facing towards the camera, and so that has to be a silhouette. Okay, there's just no way. If you take this paper here, right, it's obvious. Let's just say this is front facing, right? It's obvious that the edge, you shouldn't draw that edge. It's not a silhouette. But as you get closer to getting one side facing away from you, then you can draw the edge. Okay, so that's kind of how that works. Okay, so another thing that you can do is you could take the face normals, and you could also check to see if a threshold angle is met. So let's just say that you want to make sure that they're almost nearly, you know, maybe they're almost nearly incident, or you have some range you're interested in, and you can say, okay, draw the edge if you have some interesting angle that's met. So maybe it's like 30 degrees, or you might have to customize that based on what you're actually doing. But this is useful. For instance, let me switch over here to, I need to grab an image real quick. So I'm gonna load up in a screenshot of the shader. So let me pull this up real quick. It's almost there. Here we go. Okay, so let me pull this screenshot up of this edge surface so you can see what I'm talking about. Okay, so we can clearly see the edge, right? We have the edges on polygons that are facing, that have that flipped normal. The sign is different, but we might also be interested in edges, right, that are at a certain angle. So in this case, I think I picked approximately, I'm looking for creases, right? So the bunny is another good example. You have lots of front-facing polygons, but sometimes you would like some of the detail on the object to kind of pop out, right? So because the bunny has a lot of ridges and stuff on it, same thing here with the dragon. There's a lot of ridges on there. You'd like those details to pop out. So if you wanted to do that, you can kind of program in checking whether the face is a crease or straight. Now, if the normal, if you have two faces and they're basically identical, right? The normals are facing the same direction, you get 1, right? The dot product between the two is 1. And if they're at this direction, they're 90 degrees. So you have to basically pick which, how close would you like them? All right, so you can use the range of the dot product in that sense. Okay. So in order to do a mesh, I have an example here. You can look at some source code. But essentially, for the edge mesh, or mesh, the edge mesh, fix that here real quick. And if I can just copy and paste this image here.
So by using this normal, this differential normal detection between two coincident faces,
yes,
could it be faulted by a finitely smooth model? So if all of your little curvatures have a much higher detail mesh in them to curve them over, would that poly that system? Or?
Yes, it would. Yeah, and that's a case of, then you have to kind of plan out something a little more advanced that kind of takes that into account, right? Because you're trying to find those contours. So that might take a little bit of, you'd have to look in the research for that, but that would certainly, it kind of, as you smoothly approximate something more and more and more, the less chances you're going to get of a straight, like, hard edge there. So that would definitely be something you would want to check. Okay, so this is some source code that uses the same idea. So I have the edge here, and we have the vertex It's just a number that goes, this is going to represent an index into our vertex list. And we have the same thing for our faces. Then we also have our left normal, right normal, and we could also have a normal for our edge, right? Because the normal might represent the average of the two. So if you have two polygons, the edge could be facing, you know, the average normal, okay? So this is it. If you're trying to make thick normals, or you're trying to draw thick edges, you may want to have its own normal. That way you can kind of get a beveled look, right? Because like, for example, a lot of monitors have a smooth bevel here. So obviously that's pointing a different direction. So you may want to capture that. All right. So in this case, this edge mesh is very simple. So we just have a list of vertices, and we have a list of edges, which I use a map for, and then a list of faces. All right. So this is a very simple mesh. So rather than trying to capture a bunch of extra material information, I know that we're going to just want to draw lines. Okay. So that's kind of the idea here. So normally what we do is we'll add vertice. So we'll add vertices, but we'll basically add a face, which just represents the different indices into that mesh. Okay. And then what we do as we're looking through these, we try to find which, if we have an edge already that's using that face index or not. Okay. And so for every edge, you know that you only have two faces on each side. So this data structure is something easy to kind of keep consistent. So yeah, so we add the edge for V1 and V2. And what we do here is we just construct a unique mask, or I mean, a unique index for those two vertices. And I think over here that I just, so first I swap the vertices around if they're backwards. So I decide if it's left or right, which is important because you could V1 and V2 could, you know, you could add the vertexes or vertices in the wrong direction and miss the consistency here. So what I do is I swap them so they're in order, and then and then I just use that, you know, was it left or was it right to determine how I should put the face normal inside of this. Okay, and then I use for the indices, I can, where's that little constant here? Separation. So I basically just, this is an assumption that I'm not going to have more than 1 million vertices inside of my polygon. And I was just using that a 32-bit integer is going to store numbers between, you know, 0 and 2 trillion. And so we'll basically put the top half will be the first vertex, the bottom half will be the second vertex. So I'm just using that to create a hash. All right. So I'm just using a hash based on the fact that 1 million times 1 million is 1 trillion. So that's kind of the idea there. Okay. Now it's a bad assumption if you are going to be working with much bigger models, but for WebGL, this is, I think, acceptable. Okay. So, so we add edges. And then when we build the buffers, this is just a matter of putting the vertex information in correctly. And I just do it, a quick way is just to have a vertex buffer and then just do the GL lines, okay? So this probably could be more efficient from a memory standpoint, but I'm not, it's not really a performance issue in this case because I'm not pushing so much through the buffer or through the pipeline, okay? And then I just draw it. So it's actually fairly simple over here. And so, yeah, these are the results that that I get. Okay, so that's just an example of how you might want to do that. And then kind of going next is, you know, OpenGL representation. So we're trying to get from here, right? We have an object, and at some point we want to draw this on the screen. So OpenGL, the way the two representations that we are dealing with is draw arrays and draw element arrays. The difference between the two is that draw arrays is basically assuming you have one buffer of vertices and you just want to draw each data structure consecutively, okay? And the second one is called draw element arrays, and that's where you have two buffer objects. One stores all the vertices, the second object stores all the indices. So in this way, I could make sure that I'm not duplicating vertex information by having one consolidated list of vertices, and then the elements will point to which vertex element we want for each polygon. And then the mode represents, are we drawing points? Are we drawing lines? Or are we drawing triangles? Now, if you're using WebGL 2.0 or any modern kind of version of Vulkan, Direct3D, and so on, then you have this idea of instancing. And instancing is basically where you draw the same object repeatedly over and over again. And that is something that can get some GPU acceleration for, so that you could have like crowds and so on. They all use the same model, but maybe they have something a little bit different. And so for that, what gets passed into the vertex shader and fragment shader is an instance ID, right? So in this case, draw arrays instance, we have mode, first, count, instance count. So if I want to draw 100 of the same object, I could draw this, use this draw command. And then every time a vertex shader gets called, then GL instance ID will be 1, 2, 3, 4, 5, 6, or whatever the case is. And I could use that to decide, say, which material I want to use, or which color I need to draw, which matrix I need to use, and so on. And then vertex ID, of course, just represents which vertex number am I using for draw element arrays. Now, draw element arrays is nice, though, because you can get some caching benefit. So OpenGL is keeping track of the most recent X number of vertices that have been processed. So if you got a lot of repeated data, then it can just say, hey, I just calculated this result just a few minutes or just a few vertices ago. Let's go back and use that cached result. So this is a great way of making sure that you can get a more speed advantage by taking the fact that you've already calculated the same numbers. Okay, so OpenGL initially, when they came out, had several different representations, right? So we have GL points, and this is basically just going to draw 0, 1, 2, 3, 4, whatever the points are, it's just going to draw them in that order, okay? And then GL lines will take pairs of numbers, so like 0 to 1, 2 to 3, 4 to 5. It'll draw those pairs of numbers, okay? So that's the order that the vertices are inside the array buffer. A GL line strip will take vertex 0, 1, 2, 3, 4, and just make a single line through all of the points in that order. Then you get a line loop. So what this does is, for instance, this will draw, when it gets to 5, I think they're missing a 6 here. But when they get to 5, it'll basically draw a line back to the beginning. So you kind of get a automatic line back to the beginning again. GL polygon works very similar to GL line loop in that it'll just assume that last edge is specified for you. And then GL quads is expecting 4 vertices in a row. So 1, 2, 3, 4, 4, 5, 6, 7. I guess 0 should have been there. That's 0. For some reason it's invisible. Okay, so then this is how it's expecting the data. GL quad strip is kind of nice because you can go 0 to 1, 2, 3, 4, 5. So if you're drawing like the cylinder, for example, there's no reason to have to draw, you can cut the data that you send in half because you're not duplicating that extra information. Okay, then you got GL triangles. This one's very convenient. I use it a lot. It's not the most efficient, but it's the most generic. So you can just say 0, 1, 2, 3, 4, 5. And if you're just drawing a bunch of elements or you're throwing an element array buffer, then it's easy just to specify all the triangles for the 3D model in that one. Triangle strip and triangle fan are useful if you're trying to draw surfaces that are more, I guess, you're trying to draw surfaces that are, not just triangles. You want something more sophisticated. Triangle strip is really good for meshes, and there is actually some algorithms you can do. You can take a generic mesh and figure out how to connect it so you use just nothing but triangle strips. So you have just one draw call for the entire mesh. And there's also some tricks to getting the triangle strip algorithm to skip. So you could actually just repeat a few triangles so they basically become null. They have 0 area, so they don't get drawn. And you can basically skip around to different parts of the surface. So there are some interesting algorithms there. And then GL triangle fan is useful when you need to approximate the polygon. So I use the triangle fan. Well, actually, I normally just turn rectangles into triangles. That's pretty easy to do inline. So the issue here with OpenGL, though, is that They pretty much got rid of anything that's quad related because it doesn't make any sense. You can get into areas where you have basically inconsistent geometry, right? Because you can do this with you can fold a square, but you can't fold a triangle. Okay, and so once you do that, that has some issues. But some of these are just really useful for like terrain or 3D modeling. Like, you know, if you have like cylinders or spheres, there's definitely some advantages to using some of these other representations. Okay, and but we have to, you know, keep note that if you're trying to preserve, if you're trying to share as much vertices as possible, because you want to cut the data down, there are some consequences to that. So one of the consequences to that is, you know, when you're going to draw your object, then whatever properties are associated with those vertices are, you either have to make a choice of, am I going to share this across the entire face, or am I going to interpolate this data in between the vertices, right? So one popular method of kind of sharing light calculation is the Gouraud shading method. And Gouraud shading basically says, let's calculate the light contribution at each vertex, and then we'll just mix the color from vertex to vertex. So in this case, we're trying to approximate the Phong shading model. And you can see that the polygons kind of give away the fact that you're interpolating this data polygon to polygon, rather than calculating per pixel what the actual shading value should be. Now, if you're kind of dealing with a low, you know, you don't have a very big budget for drawing, then this is certainly a great method of avoiding calculations per pixel when you can just use them per vertex. Okay, and there's essentially three kinds of ways to share the data. One's called flat shading. That means you just use the entire calculation for the entire surface of the polygon. The other one's Gouraud shading, where you interpolate between the vertices on a per pixel level. And then the second one is perspective correct interpolation. So the reason why this looks all kind of funny, if you look at Gouraud shading, it's because it's not perspective correct. That needs to be addressed when it comes to texture mapping, because then your polygons will look all skewed. If anybody's played any PlayStation games, you'll notice this effect, because they interpolate texture information. So I guess that would be useful to see. Maybe I'll let's look at, maybe I could find something of Tomb Raider and show you. I think I have to put PS1 here. This one might be a good one. If you can see the side over here on this, well, maybe that isn't a very good one. Maybe I'll try and find another example. Maybe this is a little easier to see. Okay, so what's going on over here, if you look over here, this should be a straight line, but it's actually like, it goes this way, then it goes this way, then it goes this way, then it goes this way, and you get these like jagged edges from the shearing that happens when you are interpolating the polygons. So another way of doing it, you could look for affine texture warping. And here's a good example here. So affine texture mapping, there's no perspective cues. And then if you do perspective correction, then you notice that it, you know, disappears where it's supposed to. This is here's another example what happens when you're just trying to do this. You have like one polygon, one side of the polygon shearing left and the other one shearing right. And so then they look, you get these funny patterns inside your final image. Okay, here's another good example. Okay, so this is something you have to correct for with perspective correction, which is not something you can do. You have to do basically a divide per pixel to figure out where it should be, okay? So Gouraud shading, this is kind of what happens if you interpolate texture coordinates per pixel instead of doing a perspective correct. So that's technically a different kind of interpolation. Okay, so modeling. So this is, obviously it's typically done with a 3D program. Blender is pretty good for that if you're looking for open source. 3ds Max and Maya come from Autodesk. Maya has been used, it used to be called Alias Wavefront, and that's the same kind of software they use to make the movies. Jurassic Park was kind of done in that animation package. Lightwave is another modeling package, and there's lots, there's tons. And then I mentioned AutoCAD because, like I said, it's a different approach if you're doing solid modeling versus surface modeling, which is two different things. If you're designing an engine part, you would not use surface modeling. So 3ds Max is not the appropriate tool for that kind of thing. And then modeling software uses scene graphs. So we're going to talk about scene graphs here in just a little bit, but they use it to store information about the current animation using keyframes. And every object can basically have its own transform, and you can put those transforms objects beneath others. So you create this hierarchical transformation system. And the other thing about modeling packages, they typically let you use curved lines and surfaces out of the box just to kind of put things together. So if you're going to target a basic subset of OpenGL that doesn't have tessellation capabilities, then you need to figure out a way of basically turning it back into triangles. And just about any modeling package will be able to like turn them back into triangles. You can see the cow over here. This is a little bit older screenshot of this is kind of a famous cow graphic, but you can tell that this is a triangulated mesh inside this package. So that's typically how you want it to get. You want triangles to be output, and you want it to make sure that all those vertices are being shared so you can take advantage of any kind of edge algorithm that you want to draw. And then this also kind of shows, if you look in the shaded area on the graph, that you have different surfaces. So like the feet on the cow are something you might want to draw a different color. So if you were thinking about, our object representation here, right, then is basically have surfaces. The surfaces will have material information and so on associated with them. Okay, so let's take a look at some different applications, all right? And so 4 applications that I thought would be interesting to look at are, we'll look at examples of sprite and tile graphics. We'll look at different scene graphs and 3D meshes, how you might manage a simple algorithm for getting those rendered. Talk about collision detection and collision response, all right? So these are all things that would require you to kind of understand how objects are stored and organized in order for you to accurately or properly handle these types of situations. So the first one, sprites and tile graphics, we took a look at the Atari 2600, especially in a homework situation. And we kind of looked at, it's very simple, right? You have this player graphic, this missile graphic, and this ball graphic. People have been able to do tricks with those because you can control those on every scan line, right? So you're not just limited to just like a single pixel or even just a single pattern. You can make complicated patterns out of them. But the idea here is that it's very simple, right? You just want to throw a few things on the screen. Maybe you don't have hardware acceleration for anything. All right, so this is one way that you could kind of handle the architecture there. I think it's a great way to handle a very simple game, just because it's very it's easy to implement, it's easy to debug, and you're pretty much can have this written in a couple hours. The second approach kind of takes the hardware sprite capability influence from like Nintendo or Super Nintendo, and you can kind of go all the way to Game Boy Advance and look at the hardware, and they basically just copy this pattern over and over again. So basically what you have is this object attribute memory, and you have tile memory of 2 things. So OAM and the object attribute memory, you can basically store where these sprites are located on the screen very easily. In fact, like say on the Game Boy, that would actually have 40, it would take 4 bytes per object, and you could have 40 of them. So that's 4 bytes times 40, 160 bytes to store the positions of 40 sprites. It's pretty good use of memory, and you can definitely process that very easily. And each object, you would have the X, the Y, whether it should be flipped X or Y. So these are bits, right? So you can take these and flip the bits. Which tile is it using and which palette is it using? And they even did a few tricks. So if X and Y were both 0, for instance, then that would mean that object's turned off. It doesn't get drawn. And then there's another one that has to do with a priority. So whether it gets drawn on the background layer or the front layer. And so, but when you make shortcuts like this, though, it does have consequences. So if you've ever played an old NES game, you'll notice that on the right-hand side of the screen, the graphics are kind of like flickering. They got this like strange color going on. And that's just because when you're showing the tile, the way the graphics draws left to right, anything that's kind of technically you're drawing the object on the right with what it's I either have this backwards or not, but the object on the right is getting drawn with a different palette, the same palette as the one on the first. So if you're using different colors, then you get a flicker. You get a different color set applied. So that's why it looks weird. And then 2, you can't technically put a sprite up at the top of the screen. That's at the very top. You have to go 1 pixel down. So there are some, but I'm sure that they're delighted that they could actually, have the hardware acceleration for this despite that. Okay. Plus, like I said, it's very simple. So this is, I like to use this concept when I do games sometimes. I'll just allocate a giant array and just say, here's all my sprites, and then I can turn them on or off. I don't necessarily limit myself though to having like a specific size. I can say whatever size they're going to be, but I use that idea of like, okay, let's stick all our objects in one part of memory. And then you have tile memory. So you can set the width and height, right? Because you're dealing with cells, and then the cell width or cell height will allow you to just draw a bunch of square tiles on the screen. The other approach is the BitLit approach. And the idea here is that this is going to copy basically a block of color data from one area of memory to another. Okay, so the source, this is something that kind of got popular in the 90s because you're not limited to, basically use hardware acceleration to say, hey, let's just copy this whole rectangle to this other rectangle in memory and just do it quickly. So it's kind of a generalized version of a sprite. So you basically say, here's my X, Y in the source image and the width and height. So CX is the count in the X. So count of X pixels, CY is count for the Y pixels. And then you just say, where do I want, sorry, getting dry. Where do I want my sprite to be drawn then in the screen? And what this lets you do, obviously you can probably think about the Atari 2600. You have technically 8 bits for the sprite that you have to reprogram every line. So if you want to draw a frog or you want to draw a person, every time it's called racing the gun. Every time that the screen is going to get drawn left to right, you have a certain amount of time before the beam is basically going to be starting to draw again. So then you have a little bit of time to reprogram what those 8 bits are. So that's how you can draw like a person or a frog on an Atari 2600. That's how you get around that limitation. Okay. So then you look at the Nintendo approach and you're like, okay, instead of having to do that, I can just use these 8x8 sprites, and 8x8 is, is pretty good. But if you take a look like a sprite like Mario, then you're talking like 8x16. They're normally like 16 pixels wide by 16 pixels tall, or some multiple of 8 there. So then what ends up happening is that, on a Nintendo, which I think they give you 128 positions in the object attribute memory, but normally you're thinking, wait, so that's one sprite. But if you're drawing like a full, tall Mario, you're actually drawing 8 sprites because it's 1, 2, 3, 4, 5, 6, 7, 8 because they're all stacked because you're dealing with this 8x8 resolution. And so quickly, you might have 128 objects, that theoretically the hardware is doing for you, but then you only really get like 32 sprites or 16 sprites. So it actually, becomes a limitation because now you're working on how do I manage an animation or sequence or something like that. And then BitLit is kind of the other way around. It just says, let's just generalize the problem. You can lay out all of your images in memory. And then when you BitLit, you don't have to worry about that they have to be like 8x8 or 8x16. Okay. Okay, so here's a little bit of an idea of how you might want to do that. So I use BitLit because BitLit is basically, we can translate that to an OpenGL call if we wanted to. Or if you're using Direct3D or SDL, then you can just deal with services in memory and you get, because it's being accelerated with the graphics hardware, that's something you can easily do. So in this case, let's say we're going to do the whole screen. We're going to draw the whole screen, right? So we have a bunch of tiles. We have our tile window, and let's say that that's 8. The tiles are 8x8. Then you can say, well, what if you have several backgrounds, right? So if you wanted to do like parallax scrolling, where you're scrolling different layers at different speeds, so it gives a semblance of distance. So we can have several backgrounds. We'll draw them bottom to top. And so we'll go ahead and draw the tiles. And as we go through each one, then we'll check to see, is that tile visible? So maybe it's clipped off the side of the screen. You don't want to draw it. Or maybe it's just invisible. So it's a transparent tile. Okay, and then you can just BitLit using the information in the tile information that says, here's where it is located in the source image. Okay, and so after you draw the screen, right, we're just going to go from top to bottom, left to right. So J represents the row, I represents the column. So once we've kind of gone, we've drawn all the tiles, then we can draw the sprites on that layer. Okay, so we're compositing this together. And over here, we might have another vector of sprites over here. And in this case, let's just say that the maximum number of sprites is 40. Then we can just go through all the sprites there. And if the sprite is visible on that particular layer, then we can BitLit that sprite to that position on the screen. Okay. And so if you want to support something like flipping or rotating, then that's something you would do at this point. Figure out, how do you set the texture coordinates or whatever the case is. Okay. So that's an idea how you might do a pretty fast and simple tile graphics setup. All right. So let's talk about the 3D case though, right? So we have a good case for how to do 2-dimensional graphics, but let's think about how we might want to do 3-dimensional graphics. So some of the choices you might have to make are, are you going to use a single shader for everything? And that's called a monolithic design. And it's actually pretty useful to do it this way because if you have one shader to kind of handle all the different cases, then you're not worried about tracking which shader that you're using at that particular time. So I think it's a good approach for a basic 3D engine. And then then you have a bunch of objects that you want to draw. So the simplest way to do 3D graphics, just have a list of objects and just draw them in order. So you'll want to have a world matrix for each of them, and you'll want a list of surfaces for each of those objects. All right, matches what we've been talking about so far. So before you draw all the objects, you probably want to set some uniform variables for the entire scene. So these are things like the projection matrix or the camera matrix, because those aren't going to change for all the objects. If you're doing shadow mapping, you may need to put some shadow matrices, configure that for the shader. This is also a good time to put light positions or environment maps, things that are going to be shared by all the objects, okay? And then you're going to iterate over every object, and you'll set uniform variables for those particular ones. And then for every surface in that object, then you can set the material properties, and then you can draw the surface. So thinking back to our cow graphic, the feet, that's the time that you would set the color for the feet, for instance. Okay, so that's like the quick code this in a couple hours method for drawing 3D objects, which is something we've been doing. That's kind of what we were doing last week. Okay, so the other approach is maybe you want to use a simple grid of tile indices. So we want to take the tile method that we learned about for sprites and tiles and apply that to a three-dimensional context. So we could basically use each tile to represent. It could either represent like an actual like texture map, or it could represent some pre-built geometry that's already been done for us. So if you've ever taken a look at how a game like Diablo is put together, or a game like Neverwinter Nights, they typically have these, the 3D artists will create these whole 3D tile sets, essentially. And then you use the grid number to say, use this tile for this particular area. So in the same way that you can do two-dimensional graphics, then you can just go ahead and construct the your 3D mesh using tiles, basically. Okay, so you can do that. Let me show Neverwinter Nights editor. This is something I did a maze game in once, and tiles. Let me search for. This might be a good graphic. Okay, so over here you can see that they basically just have repeating chunks of tiles that you can just draw into the editor. So you're a level designer. You don't want to. You're not like caring about putting vertices down. You just want the stuff to be like, okay, I have my grand vision. Please let me just do my grand vision. So you'll see that tiles are actually a really popular way of building this kind of stuff out. Okay, and then you can use some algorithms though to determine whether you should automatically make a corner, right? So just like you would if you're making a text mode and you're using box drawing graphics, you can pretty much decide if you have two contiguous walls, yeah, let's go ahead and make an L section there, and so tile sets are often built up in that kind of way. Okay, so I like to call that the roguelike approach to making scenes. You just use a grid, and you can use that grid to look up either static geometry that you want to draw there, or we'll see this in the Wolfenstein approach. But the next one is to use Wolfenstein as an approach. This one uses ray casting to determine the wall shapes. All right, and then they also use sprites to represent the actual entities inside the 3D engine. Although it's just easy, it's plenty easy just to have a 3D model. But if you only have animated characters with a sprite and you want to draw them like from 8 different directions, then you can just figure out which way. It's called billboards. Which way should the sprite be facing you so that you draw. So it's always facing the same direction. So, for example, this pillar will always face the same direction no matter which way you look at it. But you may notice that the floor and the ceiling are the same color. There's no change there. And you notice that the walls are always the same height. There's no change. And so what's basically happening here is we have the grid again, and we can just say if the grid is being filled in or not, and we can use ray casting to decide whether or not we can just, well, you don't have to use ray casting. You could use some other algorithm to decide if you should just draw a rectangle there, right? But ray casting will basically say, hey, which of these indices or which of these tiles are visible, okay? So this is one approach. This is still two-dimensional, but this makes it easy. You can make this in a text file if you wanted to, and then just construct a 3D surface out of it when you run your program. Okay, so one of the next approaches you could try is, I like to call it the Doom-like bright or dark. And then you can say, here's what the texture should be on the floor, and here's what the texture should be on the ceiling. Okay, so that covers your floor and ceiling. And then you have these line defs. And what the line def does is basically connect the vertices that say, what the walls ought to be, okay? And so the wall is going to basically go from vertex 1 to vertex 2. it references the sector, and then it uses a, well, actually this should be, let me change that real quick. Side def. Okay. Oh, back. Okay, a side def. And so what a side def is, basically it's going to say, here's what the texture should be at the bottom, here's what the texture should be in the middle, and here's what the texture should be at the top. And what this allows you to do is if you have two sectors that are not the same size, right? So maybe you have a tall sector going to a small sector. Well, in the big sector, you might have a top and you might have a bottom, and then you can skip drawing the middle. And so this is a way of handling the case of several different, you have basically, now you can add height in a general way to your entire level, okay? So that's what these areas are doing. And I wonder if there's a way of, that's a little easier to see, okay? So this is exactly what they've done over here. And you can see where they're using lower textures or upper textures, like over here, the computer area, down here on the floor area, and then the carpets basically are what the floor textures and ceiling textures are. So this is how they got around to representing scenes in Doom. And then they use a binary space or binary partition tree to decide whether or not you're colliding with. So they basically determine which sector you're in, sector that you're in, and then you can check to see if you're colliding against a line. So you just have to do point versus a line collision, or a sphere versus a line collision, and then you can decide whether you're still in the level or not. So that's a great way of handling whether you're in or out. Same thing with Wolfenstein. You can kind of do that with the, are you in or out? That's how you do collision detection. Okay, and then the next approach, because this is still pretty limited because you can't have like floor over floor unless you design that in. So the next approach essentially is brushes, and brushes has pretty much been used since Quake to do 3D modeling for games. All right, so if you use Unreal Engine, you basically construct things out of solid objects, right? So, and those objects can either be inverted or they can be normal. So you would use an inverted brush if you're trying to carve area out, and you'd use a regular brush if you're trying to add area in. So this uses constructive solid geometry, one type of it. And so like a level editor would be, you just are constructing these simple shapes. Typically they're just convex shapes. And then this represents whether or not there's, I think maybe red represents this current selection, but basically you can use it to carve areas in or out. And then when it's all done, it'll build a binary space partition tree, which represents the entire level. And that's useful for creating a draw order if you're doing it that way. So you can automatically draw back to front or front to back. And with a Z buffer, you want to draw front to back. And then it's easy to check collisions because, anytime you see binary tree, just think I'm getting log, O log N kind of performance. So it's very quick to do a search to see whether or not, where are you inside this whole level and are you colliding with it or not? Okay. And then this is a complete 3D environment, so you can use this to fly through, do anything you want with. It doesn't have any of the limitations of using a two-dimensional set. But as you can imagine, brushes are a lot harder to do. So sometimes what people will do is just like, well, I'll just implement the renderer for a brush system, and then some people are crazy enough to actually build a 3D modeling tool out of it. So typically you just use somebody else's tools for creating those models. Okay, it's not hard to do. It is a little complicated, but you can definitely work your way through brushes if you want to. I once made a Quake 3 level viewer. It would just open up the file, and then I would put all the polygons where they're supposed to be. And then I would look up all the light map information so I could draw what the illumination was calculated, or the pre-calculated illumination. Okay, and the last approach here is it's typically used with just about everything. Okay, so a scene graph is extremely important. This is not the first time we're going to take a look at the scene graph, but we're going to take a look at a very simple kind. And this is a type of what's called a directed acyclic graph. All right, this is an essential term for you to remember, a directed acyclic graph. And what that means is that it's a graph that doesn't have cycles, one, so it doesn't, you don't have like one node going back to another. And then two, it's directed. In other words, you have a start and you go towards an end. So if you can imagine a tree, you know, that kind of grows in your front yard, you have a root, the main, the trunk of the tree, and it goes into branches, and you eventually get leaves. That is the same kind of idea as a directed acyclic graph. So typically your branches don't go, unless it's rare, don't go back into each other and grow into each other. They typically kind of go out. And so what we use that for is to get a back to front order. And that's how SVG works, for instance, right? So you want to draw back to front. And an example of a scene graph is the X3D specification, which evolved from the virtual reality markup language. And it's basically an XML way of defining stuff. X3D is just one example of a scene graph, okay? The main point to using them is that you can maintain the drawing order that you want, but probably more important is that you create a hierarchical structure of everything inside your scene, okay? So even a 3D engine like Unreal or Quake is going to use a scene graph of some kind. If you can imagine this scenario, you want to support vehicles inside your simulation, right? So a vehicle is fairly complicated. So you'll have like the body of the vehicle and you've got 4 wheels. So instead of having to model like 4 different kinds of wheels, you'll just use the same wheel and you'll just say, this is the individual transform that's associated with each tire, right? Each wheel. And then you'll say that the parent object is the body. So all you have to do is move the body and the wheels go along for the ride, right? And so that's a way of using a hierarchical structure, right? Just in the same way that if you're using your file structure on your computer, right? If you're going to move like a whole set of documents, you can just move the folder from one place to the other, and you know that the files will go along for the ride. That would be kind of awful if it didn't. Okay, so that's exactly how a scene graph can be used. So a lot of times you'll have, so we'll call them parent and child nodes, and we'll call those nodes at the end leaf nodes. And there's a few general kinds that we can do. So one minimum is you should have a group node. A group node is just a generic node that can store children. All right, child nodes. So the root of a scene graph would be an example of a group node. And in that, you could even have some special types of group nodes. So a selection group node would be the kind of node that only allows you to pick one of the children instead of all of them. Or so if you had like a traffic light, right, you might want to set the properties for red, green, and blue. Or not red, green, and blue, but red, yellow, green. And then you could say, okay, select red, select green, yellow, select green, right? So you could use a selection node to make sure that only one path goes down the loop. So it's like a state machine. And then you have sequence, which could be useful for animation purposes. So maybe you have several different poses you're trying to go for. So a sequence kind of group node would allow you to accommodate something like that. Then you have a geometry node. A geometry node would be associated with anything that's drawable, right? So a 3D model, a 2D sprite, a font, some text on the screen, that might be something that would fall under geometry, something you can actually draw. And then lights and cameras, those are kind of self-explanatory. So if you want to place a light in the scene, you can set it wherever you want. You can set the type, and this is something that's very applicable to object-oriented programming. So you can create a class structure around these basic types. Okay, so that's one of the popular ways to do this. My suggestion is don't get too frisky with this. Just keep this as simple as possible, and you won't run into much headaches. Okay, so as an example, this is a scene that was done in X3D, and they have a control allowed for changing the sun position. And you can see the helicopter here. It's got a rotating rotating blades. And so you can tell how this would be very useful for simulations, all right? And, or just for sharing a concept with people around the world, okay? So X3D is something that is a standard. It's basically just a simplified version of Vermal, and it's still a little boring, but that's it's still an effective way of communicating ideas, all right? This was kind of nice though, because then you can write, your scene graph library can be flexible. It can like dynamically load objects as they need them. This is why it's very common. Open Scene Graph is a common library that implements this kind, but Unity is a type of scene graph. Unreal is a type of scene graph. And generally anything that's going to do data, that's going to move data back and forth between a 3D package and a game package will typically support some kind of scene graph information. Okay, so moving on from scene graphs, let's talk about collision detection and response. All right, this is particularly useful, I think, for this coming week because Ludum Dare starts on Friday. And so there's a few functions that you might want to do, or at least get some experience with. And this is basically axis-aligned collision detection. In other words, you have a box, and it cannot rotate, right? So you have two X planes, two Y planes, and two Z planes that define the corners of the box. Okay, so if you have any two sides, if they overlap, if one plane on this box overlaps with the other object, then you know you have a collision. Okay, so one way to do this is you can write a function, do objects collide, and then A and B would represent the two objects that you're interested in. So maybe you have a list of objects like the object attribute memory, and each one then would have its own bounding box. So the minimum that you need to support is what's the minimum point in the box and what's the maximum point in the box. And size can even be a method that just subtracts the two from each other, right? So you have X1 and X2, Y1 and Y2, Z1 and Z2. That's basically the idea here. And in order for you to check to see if you have two overlapping sides, then we need a function, and I'll call it this one, is within. And this basically says if you have A, and that's the left-hand position and the width, and if you have object B's start position and the width, then by doing this comparison, right, if A is less than B plus BW, in other words, if X1 for box 1, so let's take a look at this this one. So we'll say A is the blue box and B is the orange box. So we'll say if A is less than B plus BW, so that's true, right? So A, this left-hand side of the box is clearly on the left-hand side of the right side of the box for B. So then the next thing we need to check is the right side of the box on the right side of the left-hand side of box B. So we check this side, A plus AW, and we say, is this greater than the start for B? And so we can see that this is on this side. So yes, there is an overlap in the X direction. So, but just because they're overlapping doesn't mean that they're overlapping, right? We got to check the Y direction as well. So we'll check the Y direction. So we'll say, let's take the first. So we'll just go counting down like it was, pixels on the screen. So we have X at the top here that's not on the bottom of box B, okay? And we have the bottom of the blue box is beneath the top of box B. So we know that there's an overlap there. Okay, so now we have two overlaps. And so that clearly means that there is a collision because we are overlapping in at least in all of the areas. Okay, so that's one thing. They all have to overlap in order to have a collision. So it's trivial to add the Z direction because it's the same algorithm and they have to all be, everything has to match. So the idea here is that if A.pmin, so if that represents your lower left corner and size represents the width and height, and pmin is the lower left-hand corner and size is the width, then you can check to see if there's a collision, okay? So that's collision detection, but once you have determined there's a collision, you have to have a second part, and that's response. Okay, so in order to do that, we are basically answering the question, okay, so what happens when a collision is detected, all right? And so this question I pose, are the objects enemies or frenemies, okay? So this is something to think about. In other words, if you look at Super Mario Brothers, that's pretty easy to think about because if a Goomba hits you, then that's clearly an enemy, right? But what happens if you fire a fireball and it bounces off a pipe and comes back to you? Well, then does that damage you or not? So that's what I call the frenemy. So you have to make a design choice. If the player's missile hits the player, what happens, right? So you have to decide whether to do something about that. Now, generally, collision detection is O(n) squared, but I feel it can be worse than that, depending on how you handle that. So you want to try really hard to make sure that it is n squared, but you do have problems where this can go out of control. Let's just say you have a box that contains all the objects inside the screen, all right? But you have too many objects inside the screen to fit in the box, right? So in the real world, this is like you trying to get the most out of a post office flat rate box, and you're like trying to squeeze it in there, see if it's going to fit. Okay. And generally the box has a little bit of give to it. You can kind of stuff it, but this doesn't happen with computer graphics. It's very rigid. So what ends up happening is that you'll as you're moving objects around in the scene to make sure that they all fit, then sometimes you end up squeezing one and it pops out, or you get weird, strange errors, or you just keep going in a loop because technically there's always a collision, okay? So collision detection is O(n) squared, but I think it's worse when none of the objects fit inside the box. And so, right, it's actually really easy for this to happen. So here's one possible way that you could handle this. So let's say you have all the active objects in the scene, okay? So you're gonna iterate over them. Well, the first thing you probably wanna do is make sure that the objects are obeying the rules of the environment. So you want to check the scene for collision. And then if it occurs, then just move the object to a safe distance. This is generally how you handle movement in a 3D game, right? You just check for collision and you just move them to a safe distance. And as long as you do that, then you can ride along the walls and you don't generally go through the scene geometry. This also means that you should try very hard not to have walls that are too thin, okay, and then next to each other, right? Because then you could technically, if you're going at fast enough velocity, you go to your player position, hops on the other side of the other wall, and then you are wall jumping, okay. We should watch the trucker video. That'll be fun. Okay, so once we've done that, then we should be able to check the collision with other objects, all right? And so if an acceptable collision is detected, in other words, if this is it's okay to touch, right? You have two players inside of a FPS that are touching, right? That's okay. Just move the objects a safe distance away from each other so they're no longer colliding with each other, okay? And if it's an enemy collision detection, then go ahead and handle it in some way. So maybe you need to reduce health points, or if it's maybe you're writing a 3D modeler, you make sure that the objects just don't touch each other, or you change the color of the objects so you know that there's a collision. Do something, right? You can do something about it. And then if any movement occurred, then you can either defer it to the next frame or recheck everything. So technically, if you moved objects in this loop, it's possible that you stopped the collision of one object with another, but then you created another collision with another object, okay? So this is where I say it could be worse than that. So one of the ways to make sure that this doesn't happen is you could defer to the next frame. So you only do one O(n) squared check per frame. But that has a tendency of rippling collision detection through your objects. And essentially when you're moving an object instantaneously, you're creating an impulse. And sometimes this is how objects get an extra velocity added to them that didn't exist before. So, or they'll just get shoved right out of the scene. I've seen that happen doing a naive collision response routine. Okay, so the other option is just recheck everything. So just keep checking until you have no more collisions. Okay, so basically move everything around until that has stopped. So let's take a look at an example of this. Okay, so an example of this would be, I want to say, let's go here. Okay, and there's some funny business going on over here, but what I'm going to do is I'm going to throw the size of all these objects, so they're very large. And initially there's this ripple effect, because I basically just, they're trying to repel each other, but at the same time, I'm also checking to see if they're colliding. All right, let me get another one. Operators. Okay, here's one I can control. I can set collision detection on, and I can set the number of object to something large. Okay, so over here is a case of, if you notice at the beginning, they're all kind of shuffling around each other. But what you end up seeing though is some objects, as they're trying to move past each other, if you don't do it quite right, you get these like strange bugs where suddenly they're zipping past each other at ridiculous speeds. And it's not realistic. So this is a bug in this particular code I did not fix because I wanted to kind of show that off. Let's see here. So if you notice when I first started, there's all this jumbling around, and that's because I'm checking collision detection, and then I just wait till the next frame. And so what ends up happening, you get this ripple effect as you're checking collisions, which even with 500 objects, that's not too bad for real-time performance, I think. So that gives you hope that on any modern computer you can handle just worst case scenario collision detection and probably be okay. Let me see if I have another example. I think that's what I had there. Okay, so
in that simulation, it looked like there were primary objects and secondary objects, and the primary, or at least how I was interpreting it, would kind of like tunnel through the others. Yeah, well, what happens? Okay, I see. Yeah. I can turn it on or off, like whether the collision detection is happening. So if I'll put 40 objects in there. What I'm just noticing that the objects in motion push the stationary objects out of the way. Yes. Yes. The velocity is not changed. I feel like I have another one, or maybe I have to do it with this. I got to turn that down and that up. So there's the ripple effect very, very clearly. And then generally they're doing okay unless I have some objects moving around. And when they're all like in close quarters, you know, there's a certain elasticness about this particular simulation. But if they can get a little frisky in there, and as they're moving, because it's a choice. Do I determine velocity based on actual movement, or do I do velocity based on what they were the last frame? And so that is a big deal, though, because if something, you know, you have to almost make a intentional choice to have collision. You can see that one just kind of like, oh, that's me doing. I can move the mouse and move one of the particles around just to kind of demonstrate. Okay, so. You know, and then you know, if I'm trying to push it down, then it's going to like not move until it can move. Okay, so collision detection is not like the easiest thing in the world, but you know, that's why if you keep your numbers small, then generally you can kind of find out when it's causing problems and when it's not.
All right. And then just make sure that you don't have any initial conditions that are just going to like go crazy on you. You know, like this is an example of how not to like set initial positions, because you don't know technically where everything's going to end up at the time. All right. Okay. I did want to show you a video of, and hopefully it's in my, not iceworks records. Okay, I'm gonna look up collision detection, and there's an example of a particularly bad video games. Big rigs over the road racing, which is a funny video. So we'll watch this because I think it hammers in. There it is, best video game ever made. And I think actually I need to get in order to get the audio. I don't know if this video doesn't play online, then no, it should. It should play online. Okay, so let's go and watch this. Okay.
Big rigs over the road racing is one of, if not the best video game ever made. Not just the best racing game, not just the best PC game, the best video game ever made. First of all, the graphics are amazing. A lot of times I felt like I was like in the real world. Like this is a virtual reality machine that I stepped into, because everything looks absolutely stunning. And if you put your graphics on the highest setting, it's really gonna feel like real life. Like you'll be playing the game, and once you take your eyes off the computer screen, you'll think you're still in the game, because the graphics of real life and this game look exactly the same. Look at that grass. I mean, that's exactly what grass looks like after a rainy spring day. Just dew all over it, flashing in the beautiful sunlight. God, a lot of times I won't even actually race. I'll just drive through the levels and just look at the pastoral scenery. This game isn't so much a game as an experience, a wonderful experience, an experience of pure euphoria. Now, my game didn't come with sound effects or music. I'm not sure if they're supposed to be in the game, but I think that's so fantastic, because a lot of games have really annoying good music and sound effects, and that really takes the focus off the gameplay. You know, when you're playing a game, you need to focus on what's important, the gameplay. When you're focusing on trivial things like story or music or sound effects, it's going to take you out of the gameplay, and you're not going to appreciate the gameplay as much. Now, one of the greatest things about big rigs over the road racing, what really makes the game stand out from other racing games, is the versatility of your truck. Your trucks aren't just little weak, worthless trucks that have to follow the road and they veer off the road. They're going to drive like crap. Your truck drives the same everywhere. You can drive through buildings, through lampposts. You can drive up mountains and not slow down even an ounce. It's absolutely fantastic. And there's just so many different trucks and environments for you to play through. This game has a collection of over 4 different playable trucks. That's right, 4. Big Rigs also has a ton of different levels, like Devil Passage 1, Devil Passage 2, Forgotten Road 1, Night Ride, and of course the fan favorite Small Town Road. You have to be careful though, because a lot of these maps do not actually work. And if you pick a map that doesn't work, your game will crash. Possibly one of the greatest things about this game is the competition AI. You see, you're actually racing against other trucks. In most levels, there's one other truck you're racing against. And the thing is, when the race starts, that truck just stands still. And you can literally go all the way around the racetrack. You can literally finish the race, and that truck will continue to just stand there. Now, I know what you're thinking. Well, how is that good AI? It's social commentary on racing. It's basically saying, what's the point of racing? Just enjoy the beautiful scenery. I'm not going to race you. What's the point of competition when we have these beautiful pastoral settings for you to just stroll through and enjoy? Look at those trees. Also, the bridges don't work. When you actually drive onto a bridge, you drive right through it. Some people might think this is a bad thing, but the fact is, you don't need bridges. Like I said, your truck is so amazing, it can drive anywhere and it won't slow down. There's no friction going down hills, going up mountains, going through buildings and trees. Nothing stops your truck. You can literally drive off into the netherworld and your truck will be fine. It's really durable. You know, it's been almost 10 years since this fantastic game was made. It was first developed in 2003. And I think it has really stood the test of time. You know, a lot of games, older games, 10, 20-year-old games, they just can't keep up with the graphics of today. But Big Rigs actually pioneered a lot of the graphics we see today. A lot of really complex cell shading and things like that. Big Rigs is one of the games that pushed the graphical limits of gaming and brought us to this new generation of pristine graphics. Big Rigs Over-the-Road Racing is an absolute classic. I consider it the best game ever. Some people might think it's only the best racing game or the best PC game, but I'm just gonna go out and say it is the best game ever made. It is a pure, unwavering, solid 10 out of 10. There is nothing wrong with this game. It is perfect. It is the ruler by which other games should be measured. Thanks for watching. Goodbye, my friends.
So that's my that's my favorite collision detection video, just because I didn't realize that there was a commercial game with that was that bad. So
It didn't look like collision detection was. It looked like it just passed the truck vertically down.
That's
so it would
well, yeah, and then it would it would calculate the normal from the height of the neighboring terrain, and then that basically say whatever that normal is, that's the normal the truck should be. So yeah, so basically it's non-existent collision detection, but you know, it kind of goes into, you know, what kinds of things do you need to keep in mind, right, when you're kind of handling collision stuff. But all that kind of comes into play, like how do you represent your 2-dimensional or 3-dimensional game? Like what those choices affect how you can draw, they affect you know, the kind of game that you're actually making, and so on. So I hope that was interesting. On Wednesday, we're gonna go over some more coding and talk about texture maps and buffers and the options. Kind of talk about what are all the main shading things that you would like to take into account. But we're gonna figure out how to get texture maps onto the GPU and talk about how to do things like hidden surface removal and things like that. I think that's it. Hey, perfect timing. So